What specific problem does your proposed method aim to solve in the context of offline in-context reinforcement learning, ICRL, and how does this relate to existing limitations of current methods?
Our proposed method aims to address the critical limitation of existing offline in-context reinforcement learning, ICRL methods, which do not explicitly optimize the reinforcement learning, RL objective of maximizing cumulative reward. Current scalable approaches, such as algorithm distillation, AD, and decision pretrained transformer, DPT, primarily adapt supervised learning techniques without focusing on reward maximization, leading to suboptimal policies, especially in offline settings where interaction with the environment is not possible. By introducing modifications to the transformer architecture to incorporate RL objectives, our method seeks to enhance performance in offline ICRL tasks, particularly in handling low-quality datasets and improving data efficiency. We empirically demonstrate that optimizing the RL objective significantly improves performance across various datasets and environments, thereby filling the gap left by previous methods that relied on heuristics and lacked rigorous optimization for reward. This work is the first to explicitly optimize the RL objective in an offline ICRL context, showcasing the potential for better generalization and robustness in real-world applications.
How does your proposed method work? Please illustrate the step-by-step algorithmic process, including any theoretical components that are essential to its function.
Our proposed method builds upon the algorithm distillation AD framework, utilizing a transformer architecture while incorporating explicit reinforcement learning RL objectives. The algorithmic process begins with encoding each step of the agent's experience as a tuple, state, previous action, previous reward, which is then concatenated into a single token for input into the transformer. We enhance this input by adding flags to indicate episode termination and the current episode step. Instead of predicting the next action as in AD, we replace the prediction head with value function heads that are trained using corresponding RL loss functions, and for continuous problems, we also include a policy head. This modification allows the model to optimize for cumulative reward directly, addressing the limitations of previous methods that did not explicitly maximize the RL objective, thereby improving performance in offline in-context reinforcement learning ICRL settings.
Can you provide a concrete example of how your algorithm processes input data and generates an output, detailing the inner workings through a specific case?
In our study, we utilize algorithm distillation AD as a baseline, which processes input data by predicting the next action based on a sequence of tuples representing the agent's state, previous action, and reward. For instance, in a discrete environment like the darkroom, DR, each step is encoded as a tuple, state, previous action, previous reward, which is then concatenated into a single token for input into the transformer architecture. We enhance this by incorporating RL objectives. For example, we replace the next action prediction head with value function heads that are trained using corresponding RL loss functions. This allows the algorithm to not only predict actions, but also evaluate the expected rewards of those actions, thereby optimizing for cumulative reward. In practice, when the agent encounters a state, it uses the learned value functions to determine the best action to take, ultimately generating an output that maximizes the expected reward based on the input data it has processed.
What are the key advantages of using your method over existing approaches, particularly in terms of efficiency, accuracy, or data handling capabilities?
The key advantages of our method, particularly in the context of offline in-context reinforcement learning, ICRL, lie in its superior efficiency, accuracy, and data handling capabilities compared to existing approaches like algorithm distillation, AD. Firstly, our RL-based methods consistently outperform AD across various environments, demonstrating a significant improvement in performance metrics, such as a 28% average increase in test targets with conservative Q-learning, CQL, compared to AD. Secondly, our approach exhibits greater robustness to limited target repetition in learning histories, making it more suitable for real-world applications where comprehensive data coverage is often unattainable. Additionally, we show that our methods can effectively leverage low-quality datasets, achieving higher performance even when faced with early or mid-expertise levels, unlike AD, which struggles under similar conditions. Lastly, our experiments indicate that RL-based methods can handle unstructured data more efficiently, further enhancing their applicability in diverse scenarios, including continuous environments where traditional online RL methods may falter.
How did you validate the effectiveness of your proposed method? Please describe the experimental setup, datasets used, and the metrics applied for performance evaluation.
To validate the effectiveness of our proposed method, we conducted an empirical study using over 150 datasets derived from widely used GridWorld and MuJoCo tasks, specifically focusing on discrete environments like dark room, doctor, and dark key to door, K2D, as well as continuous environments such as half-cheetah and ant-dir. We compared multiple RL-based approaches including conservative Q-learning, CQL, implicit Q-learning, IQL, and twin deep Q network, DQN, against algorithm distillation AD, which served as our baseline. Performance evaluation was conducted using the normalized area under the curve NAUC metric, which captures the progression of performance over episodes and is more robust to noise than fixed episode evaluations. We also tracked performance across different expertise levels of datasets, varying the number of unique training targets and learning histories per target to assess the impact of dataset coverage. Our results consistently showed that RL-based methods outperformed AD, particularly in terms of reward maximization, confirming the importance of explicitly optimizing the RL objective in offline in-context reinforcement learning, ICRL.
What are the main results achieved with your new method, especially in comparison to algorithm distillation, AD? What insights can be drawn from these results regarding performance across various environments and data conditions?
The main results achieved with our new method, which incorporates explicit optimization of the RL objective, demonstrate a significant performance improvement over algorithm distillation, AD. In discrete environments, RL-based approaches consistently outperform AD, with conservative Q-learning, CQL, achieving a 28.8% average improvement on test targets compared to AD. Additionally, our experiments reveal that RL methods are more robust to variations in dataset coverage and quality. For instance, they maintain stable performance even with limited learning histories, unlike AD, which struggles under such conditions. In continuous environments, the offline RL methods, TD3 plus BC and IQL, also significantly surpass AD, highlighting the critical role of offline components in handling the complexities of real-world applications. Overall, these results underscore the importance of explicitly optimizing the RL objective to enhance performance across diverse environments and data conditions, confirming that RL-based methods are more data efficient and adaptable than AD.